Okay, well, I'm going to start off with this common ion effect. This is when you've got usually what you're trying to do is remove something from a solution. So let's say that you had hard water at your house, and so every time you drank the water, it tasted like iron, or it just tasted maybe possibly chalky, or had too much texture. I know that sounds a little strange with water, but it's totally a possibility. So let's say that you had oh, I don't know, let's say that there was some iron, or you should pick a better color. Let's pick orange, since that's what it would do to your water. So let's say that you had some of this in your water and you were trying to get rid of this. Well, you could add something to the water that could precipitate this thing out. And that's the common ion effect. We've talked about it with lead and magnesium and sulfate. So if you've got this, you can throw in a little bit of, if you put in sodium carbonate. If this is a solid, when it hits the water, it will dissociate into 2 sodium ions, and then the iron will make a combination with carbonate and form a solid. So now you don't have iron in the water anymore. So there'd be you need a 2 here, and this would be a subscripted 3. So the common ion effect is a way to remove or decrease the solubility of a particular ion in solution. That way you can remove it easily with like a physical process like filtering. And there you go. This is how you remove ion from water that you don't want. So I believe we talked about lead in class. So if you had some lead in the water, I think there was a homework question before about Flint, Michigan, something like that. And if you added magnesium sulfate to this, then you'd end up with, if this was aqueous, and this is obviously aqueous because it's an ion, you'd end up with magnesium that's aqueous, which is a mineral that you would like, and some lead sulfate solid that would fall to the bottom. Which of the following dissolves the most and the least in water? So let's pull up J. So Q, text. This is way down here at the bottom. One, two, I think I went too far. 1, 2, 3. Oh, I see those numbers don't line up right. Interesting. The number here is the incorrect page number when compared to the actual book. All right, so here's some solubility products. So what we were asking about were, what were we asking about? So we want to look at lead 2 sulfate. Okay, so where's lead 2 sulfate? Oh, lead 2 sulfate is 7 or 10. We just really need the times 10 to the 29th. All right, so this one is a 10 to the negative 29th. Okay, and then the calcium carbonate. 10 to the negative 9th. 10 to the negative 9th. And the iron 3 hydroxide. Sorry. Iron 3 hydroxide. Should be up here. That's a 10 to the negative 38th. Holy smokes. 10 to the negative 38th. And then the zinc carbonate. Let's go with zinc. 10 to the negative 10th. Okay. So that's a 10 to the negative 10th. All right, so most soluble is going to be the calcium carbonate because it's a 10 to the negative 9th. And then it's going to be zinc carbonate. Then it's going to be lead sulfate. And then it's going to be iron 3 hydroxide. So most soluble, least soluble. I mean, none of these things are soluble per se, but of the things that are insoluble, the ones that are the most insoluble is this lead 3 hydroxide. All right, so if you added solid aluminum phosphate, all right, so I've got AlPO3 and solid Ag2S to a solution. Which ion will be present in the greatest molar content? Okay, well, both of these are insoluble substances, so we're going to have to check the solubility rules, or solubility constant. So silver sulfide and, okay, so is it alphabetical? So silver sulfide, holy smokes, it's a 10 to the negative 49th. Alrighty, so 10 to the negative 49th. And, sorry, what else were we looking for? Aluminum phosphate. Oh, there's no solubility rule for aluminum phosphate, so let's check it out. KSP. Looks like it's 10 to the negative 21st. So this one is 10 to the negative 21st. Which ions would be there in greatest concentration? Okay, so you'd have equal parts aluminum and phosphate, and then you'd have twice as much silver as you do sulfur, but these would be much less. So these are tied for number 1, and then this would be number 2 in concentration, and then the sulfide would be number 3 in concentration as far as the amount. Dative bond. Dative bond is, so if I've got, easiest one to do is just this ammonia and a water molecule. So the lone pair of electrons on top of this nitrogen can yank apart that hydrogen and the water molecule. So I end up with a plus charge and then a hydroxide. And what we have here is this bond right here was formed by those 2 electrons, and those 2 electrons came specifically from the nitrogen. So a dative bond means the covalent bond that was formed, both of the electrons came from one atom. And so the hydrogen showed up as an H+, it has no electrons. So when this bond is formed, it's formed because these 2 electrons, or this bond is formed by these 2 electrons over here in the nitrogen. What's the pH of 2. Okay, so 2.2 mole liter. We got hydrazine. All right, so we gotta go notes. Let's go here, acid base notes. We gotta go way up. Maybe not that far. Oh yeah, further. Hydrazine. Okay, so it's 1.26 times 10 to the negative 6th. Okay. Where am I? Here. Here. No, here. Okay, so 1.26 times 10 to the negative 6th. Alrighty, so it's a weak base. We know that because hydrazine is got a couple of nitrogens on it. So what we end up with is, well, we can just go it'll be X, X, and then hydrazine, N2H4, and this is the Kb for this. And so it's X is equal to the square root of 1.26 times 10 to the negative 6 times 2.2. All right, so where's calculator? Square root 1.26 e negative 6 times 2.2, close parentheses, and I get a 0.001665. If I take the negative log of this number, negative log u, close parentheses, I get 2.28. Sorry, 2.78, but this is pOH. So then my pH is that minus 14. So we're 1122. There's my pH. All right, that's it.